Hi everyone, welcome back to our channel. I hope you and your family members are doing good because that is the most important thing, and for rest we are here to talk. So we were following our pattern wise DSA sheet. In this we were doing three topics and the pattern was DFS pattern. Today we'll see the next question, which is maximum depth of a binary tree, and the next problem is minimum depth, which is very much similar to the maximum depth of a binary tree. So let's see the very first question from this pattern. So let's read the problem statement. It says we will be given the root of the binary tree and we have to return its maximum depth. Maximum depth is nothing but maximum height of a binary tree. So if we look at the constraint part, it says the minimum number of nodes can be 0 and the maximum number of nodes can be 10 power 4. So if you are looking for any submission which takes n square time complexity, then definitely it will become 10 power 4 multiplied by 10 power 4 means 10 power 8. And if you have watched our video for time and space complexity, where we have discussed that 10 power 8 will be slow and beyond that it might give us TLE. I'll attach the link of that complete video here. So means we need to optimize the code, and as the minimum number of node is 0, so in breadth first search we have to write the base case, but in depth first, whether the minimum number of nodes are 0 or 1 or more than that, DFS means you have to write the base case so that the recursive call will stop at one point of time. And regarding the node dot value, where it says it can go from -100 to 100, why we read this? Because the integer can hold up to value 10 power 9, and if we have to do summation or multiplication of such numbers where the output can go beyond that, means we have to store it in long format. But here we have nothing to do with the root values, so it's safe for us. So as of now we have learned about BFS approach and we have learned about DFS approach, remember? And we have to give the depth. Can I say maximum depth is nothing but the number of levels? Yes, I can, because here for this tree the expected output is 4. If you see here example number 1, you can see how many number of levels are there? 3. So the output is 3. Now for example number 2, 1 null 2. So if we draw a tree like here, 1 null and 2 means here we have null. So number of levels 2. So I can say number of level is nothing but the maximum height of the binary tree. So isn't it easy in DFS? Yes. So in DFS you all know we have learned about the binary tree level or traversal, where we write the queue while first in the queue we will insert our root. Remember? Now once we did, until our queue become empty. Now we'll calculate the size. Size is equal to queue dot size. Now for size times we have to run our for loop. For int I is equal to 0, I less than size and I plus plus. Now we'll pop all our nodes from the queue. So queue dot poll. Now we are not supposed to do anything with the node. We just have to insert their left and right children. So if node, we have popped in node, right? So if we have node dot left, then in queue we have to offer node dot left. And similarly, if node has right child, then in queue we have to offer node dot right child. Very simple. Now after that what? We are not supposed to do anything with the node or children. Okay. Now what will happen? In the queue, first this node will go 1, correct? Then we'll pop 1, correct? Now we'll insert their children 2 and 3. Now next time the for loop will run for 2 times. Okay. Now again pop 2, and now pop 3 and insert the children of 3. Now next time again this for loop will run for 2 times. Okay. Okay. So we'll pop 4. Does not has any child, pop 5, we'll insert 6 now, correct? And now next time the for loop will run for 1 time. So how many times the for loop has run? Can I say 1, 2, 3, 4? And that is nothing but the level. So we can initialize a height variable somewhere here, and after coming outside the for loop, every time we have to do height plus plus, and at the end we'll return this height. Very simple. So with the BFS approach, so we can do this is nothing but level or a traversal only, but instead of inserting our node or storing our node in some another array list which is not required here, we just need to count the number of levels, so we can simply do with the height plus plus. The similar approach we have done in our previous problems as well. So I hope this much you are aware of. Talking about the time and space complexity, we have insert each number of nodes in the queue. So O of n space complexity. Talking about the time complexity will also be O of n. N is equal to number of nodes. Why? Because every node we have popped and we have inserted their children in the, like, whatever task we did, but for every node we have run this, like, so O of n time complexity, and O of, in the worst case also, the space complexity will be O of n by 2. Why? Suppose this is a complete binary tree, correct? Complete binary tree. So this children and here also. So in the worst case, the last level has 1, 2, 3, 4, 5, 6, 7, 8 children. Total number of nodes are 15. So at max, this much level of children you will save, which is nothing but n by 2. So hence n by 2 is O of n only. So with BFS, so it is possible. How it is possible with DFS? With BFS, it took O of n time and space complexity. But before this, let's see the code in editor. So here is the code what we have discussed. First we'll check the base case. Now we'll create the queue and offer root. Depth or height we will initialize until it becomes null or empty. We'll calculate the size. We'll run the for loop for that size. Here we are just popping and inserting their left and right child in the queue if they are present. Now after every for loop which is for level, we'll do depth plus, and at the end we'll return this depth. This is nothing but maximum depth of a binary tree or maximum height of a binary tree. But how can we do this with DFS approach? In DFS, I know if I will be standing here, I cannot decide what is my length. Can I? Maximum depth? I will be waiting for my left and right to give their maximum height. So left will give 1 and right will give 3. So total height will be, can I say, maximum of left, right plus 1? Yes. So basically, if I am present at root, I'll go towards my left side, I'll go towards my right side, and I'll ask them to return me the maximum height. Correct? So basically, I can say one thing. If I have a DFS function with root, make a habit of writing this much code for sure. Okay, if root is equal to null, what are we supposed to return? Simple, integer or boolean. See, you are waiting at root to get the to get the maximum height from left side, to get the maximum height from right side. So height will be of integer size, right? So the return statement should also be integer. So when the root is null, you have to return 0. Now what? Now our task is, first we'll check, is the root null? No. So we'll go towards left or right side. So first let's go towards left side. So you will call the root.left. As you are returning integer, so it is very important to save in a integer variable. Similarly, int right DFS root dot right. This much code is so pretty much clear. So now what we'll do, let's make the stack call also. In starting, we'll make function 1. Now we'll go towards its left side, function 2. Now again we'll go towards its left side, function but null. As this is null, so it will get removed from the stack, correct? And it will return 0 to the function. So left will return 0 to 2, correct? Now similarly, right will also return 0 to 2. So can I say, for 2, we have left 0, right 0. So what 2 is supposed to return to 1? Do you think maximum of left, right, or summation of left, right? What? 2 can only return if it has path. So 2 can only return either this path or this path, correct? Like how 3 has returned. 3 has this path also and this path also. But 3 will return the maximum path, means I can say maximum of left or right and plus 1 for it, right? So what it will return? Return math dot max left comma right plus 1. Very simple. Okay. So what 2 will return? 2 will get returned and it will return value 1. Now function 1 will go towards its right side, means call for 3. Now function 3 will call for left side 4. Now function 4 will call for left side, which is null. So null will get returned and it will return 0. So from left side we have 0. Similarly from right side we have 0. Maximum of 0, 0 means 0 and plus 1 means 1. So 4 will get removed and 4 will return to 3 what? Left 1. Now 3 will go towards its right side, means function 5. Now function 5 will go towards its left side, means 6. 6 will also go towards its left side, means null. None will get removed. Similarly 6 right side null. Null will get removed. So for 6 left is 0, right is 0, so maximum of left right, which is 0, and plus 1 means 1. 1 will get returned to 5's left side. So from 5 left we got 1. Now 5 will also call for right side, but it is null, so it will return 0, right? 0. Now 5 has left and right. So what will get returned? Maximum of left or right, which is 1, plus 1, which is 2. So 2 will get returned to 6 right side. Sorry, 3's right side, correct? Yes. So 5 will get removed and it will return right 2. Why? Because maximum was 1, 0, which is 1, and plus 1 for it means 2. So 3 has left 1, right 1. So what it will return? Maximum of left, right, which is 2, and plus 1 for it, which is 3. So function 3 will get removed, correct? Yes, and it will return what? Right 3, correct? Now what will happen? Maximum function 1 has left 1, right 3. What is the maximum? 3, and plus 1, 4. So hence at the end 4 will get returned, and that's what expected also, remember? So hence at the end, so from wherever we have called this main function, we will return as it is, return DFS root. So you saw now, we just got 4 as our answer, so 4 will get returned to the main function. That's it. So what is the time complexity? We have iterated to each and every node. So O of n, where n is number of nodes, and space complexity you just saw. 1 we inserted, then we inserted 2. We removed 2, then we inserted 3 and inserted 4. We removed 4, then we inserted 5, then we inserted 6. So this is the maximum number of levels, and this is nothing but levels, which is space will be log n if it is a balanced binary tree. If it is a skewed tree means you will have a lengthy number of nodes towards any side. So in that case you will end up putting all the nodes in the stack, which is nothing but O of n. Although in the skewed tree or balanced binary tree, we are actually inserting the number of levels only. But in the balanced binary tree, the number of levels are exactly or near around logarithmic of n. But in skewed tree, it is near to linear. Okay. So space complexity in this case is log n. Time complexity is O of n. This is the DFS code. So let's write the code. So what we'll do, first we will check the base case if our root is null. If our root is null, then simply we will return 0 because integer was expected. Now we'll call for left side and right side. So integer left is equal to, we'll call the same function with root dot left. Similarly, integer right, we'll call the same function with root dot right. Okay. Now we will return math dot max of left or right and plus 1, and that's it. Now let's run this. And let's, did I miss something? Okay, sorry, my bad, spelling math.max. Now let's try to submit this. So this was very easy. I hope you all have understood this. This was the code in Java. With a similar, I hope you can write in C++ and in Python as well. So if you understood, definitely we can go in the sheet and mark the next question, which is maximum depth of a binary tree as done. Now let's do the next question, which is minimum depth of a binary tree, which is very similar to this problem. As you can see, here also we'll given the root node and we have to return the minimum depth. So if you're thinking the approach is similar, we'll just go here and we'll just copy this much line of code. In our minimum depth, we will change this code, like the function name to minimum depth and the max to min. Okay, now let's run this. As you can see, example number 2 has given us the wrong answer. Why it is so? Let's draw this tree. Okay, so if we will draw this tree, it will be like first we have 2, then we have null, then right child we have 3, left child we have null, then we have 4, then we have 5, then we have 6. It is something like skewed tree. Okay, so what it will do now? So if you'll see now, like how we did max here, so instead of this, if you'll do min, let's say we will do minimum, right? Rest all are same only. So for 2 we'll go towards left side, we got 0, correct? So from 2's left we have 0. From 2's right, what we have? If you see the number of this total 4, correct? So what we are returning, minimum of 0, 4, which is 0 and plus 1. So you will be expecting 1 as the minimum height, correct? But don't you think we do not have anything towards left? Means you will return, like you will do minimum check only when you have left child also and right side child also. But here we don't have left child. So this is the maximum node and this is the minimum node as well. Okay, so the only thing is to return the minimum, it is very much needed to check if it has both left and right child, correct? Means if it does not has left child, whatever is there towards the right side, return that. Similarly, if it does not has right child but it has only left child, so whatever is there towards the right left side, return this. But if you have both, then only do this comparison. Did you understood? So what we will do here, instead of directly calling, what we'll do, we'll check if our root, like root dot left is null. So if our root dot left is null, it means we have to go towards its right side. Okay, we have to go, like we have to return the right side call, which is root dot right. Okay, so as you can see, example number 2, I just showed you, right? So for root, we do not have left nodes, correct? So we'll simply go for right side. So what right will return? 1, 2, 3, 4. +1 for this. So we have to say +1. Okay. Now similarly, you have to do for left also. Okay, if our left is also null. So if our right. If our root dot right is null, then go for left side and +1 for the node. If nothing is null, root left and root right is not null. As you can see, example number 1, the previous code has worked. It means both of these if cases will not run. Then what we'll do, we'll go towards right side and left side. So first we will call the left side. Why? Because now left is not known. So we'll call the same function with root dot left and root dot right, and whatever will be the minimum, we'll do +1 to it. So let's run this code now. As you can see, it has run, and now we can submit this. Talking about the time complexity, it will still be O of n, because on every node we are going for only one time, correct? Yes. So this was your code in Java, and here is your code with a similar approach in C++, and here is the code in Python. So this was your DFS code, right? But if you talk about BFS code now, BFS, breadth first search, then it will become more easy, I'll say. Yes. How? See, for maximum depth, you counted the number of levels. Can I say that? You counted the number of levels. Okay. Here, the maximum minimum number of levels will be same. But if we had one more node here, let's say 5, one more node. So what will happen? In this level, you have one child. In this level, you have 2 child. Next level, you have children's. But when you pop this, for any node, you found no left, no right child. Means whenever you found your first leaf node, that level you can simply return as the minimum height. What I said. Is it leaf node? No. You will insert their children in the queue, 5 and 3. You will pop 5, you will check, is it leaf node? Yes. Now if you will not check that, na, see, 3, is it leaf node? No. 4, is it leaf node? No. 5, no. 6, yes. So 6 is the maximum height. But at first, at any time, like wherever you have found your first leaf node, that level is the minimum height of the binary tree, and that's it. So in the BFS code, how you will write? Let's see. So what we do, first we go in the maximum depth and we will copy the BFS code this much, and in the minimum depth we'll paste it, correct? Now what we have to change is initialize our depth with 1. Why? Because initially first whatever root you have inserted, that is nothing but depth 1, correct? And now here you will go, and after popping the node, you will check if my node dot left, if left child is equal to null, and similarly node dot right child is equal to null, correct? Now what you will do, we have to return the same depth as it is. Otherwise, the depth will get incremented after every level, and at the end you have to return. Anyhow, it is about minimum depth, so the minimum depth will always get returned from here. But as it is Java, so you have to return something, so that's why we are adding the return statement. Why I said that? Even if it is complete binary tree, let's say, first in the queue 2 will go, we'll pop 2 and we'll insert 5 and 3. Now you'll pop 5, and 5 is a leaf node? Yes, so you will return the total depth from here only, means this line of code only. Okay, so let's run the code, done, and let's submit this. So this was your code in Java for BFS. I hope you understood. This was very easy. Time and space complexity was also linear, correct? So if you understood this, definitely you can do in C++ and Java as well. If yes, then let's go and mark the next question also from this pattern sheet. So I hope you understood. If yes, do hit the like button and let me know in the comment section, are you able to solve this problem or not? And if you have not subscribed the channel, what are you waiting for? Go hit the subscribe button and you can even refer to your friends who want to learn pattern-wise DSA. And that's it. I'll attach my social media links and the sheet link in the description. Let's meet in another video with some more interesting questions, topics and patterns. So then keep learning, take care of yourself and your family too.